Hello friends. In this lecture series, we are discussing the part 2 of the initialization of the 386DX and the debugging and a virtual of the 386 mode. This one is the part 2 of this lecture series. The TLB translation look aside buffer TLB testing. The 386 provides a mechanism for testing the translation look aside buffer. It is the cache used for the translating the linear addresses to the physical addresses. The cache which is used for translating the linear addresses to the physical addresses, as a failure of the TLB hardware is extremely unlikely. So including the TLB confidence test among other power up confidence test for the 80386. A TLB testing, that means a translation loop aside testing. So this mechanism is provided for testing the translation. That is in 80386, there is a special mechanism for testing the TLB buffers. It is the cache used for translating. So TLB is nothing but the cache used for translating the linear addresses to the physical addresses. If the failure of this TLB hardware is so much unlikely, so to include the TLB, so the TLB confidence test is included with the other power up confidence test for the 386. It is recommended to turn off the paging bits 0, PG is equal to 0. How the structure of the TLB is there. The TLB is a four-way associative memory. The tags are the 24-bit wide. They contains the higher order 20 bits of the linear addresses, the valid bit, and three attribute bits. The tags which are used here are the 24-bit wide. They contains the high order 20 bits of the linear addresses and a valid bit and a three attribute bits. Data portion of the each entry contains the high order 20 bits of the physical addresses. The TLB is a four-way set associative memory. Data portion of each entry contains the high order 20 bits of the physical addresses. Test registers. The two test registers for testing the TLB. There are two test registers for testing the translation look-side buffer TLP. These are the TR6 and a TR7. These are the two registers for testing the TLB. TR6 is the test command register. TR6 is also known as a test command register, whereas a TR7 is a test data register. Test registers are privileged resources accessed at the privilege level 0. Test registers are privileged resources which are accessed at a privilege level 0. As shown in the figure, the structure of the TLB is shown here. The tag bits and data bits are of the test registers are shown here, TR7 and TR6. The 00 bits and physical address is of the 11 to 31 bits, whereas the linear address is also of the 11 to 31 bits. So HT bits in a TR7. A test command register TR6. It contains the command and an address tag to use in performing the command. C is the command bit. C is equal to 0 for a TLB lookup. C is equal to 1 for a TLB write. C is a command bit. If C is equal to 0 for TLB lookup and C is equal to 1 for a TLB to write. V is a valid bit, that is a TLB entry. A TLB uses a valid bit to identify the entries that contains the valid data. D is the dirty bit for or up from the TLB entries. So another is a D hash. Okay, D is a dirty bit for TLB entries, or D hash is a dirty bit from TLB entries. U or U hash is a for or US bit for the or from the TLB entries. W or W hash, the read write bit. Okay, for this is a W is a read for the TLB entries, and W hash is a write bit from the TLB entry. X and X hash as shown in the figure 00. The effect during the TLB lookup is undefined. So when X and X hash bits are 0, 1, they match. If X is equal to 0, the bit X becomes 0. If X is 1 and X hash is 0, the match. If effect during the TLB, if it will match with the TLB lookup, if it is X is equal to 1, bit X becomes a 1. A test data register 7. It contains the command and an address tags to use in performing the command. Physical addresses, data fields of the TLB. For TLB to write a TLB entry set to this value. For TLB lookup, HT is equal to what TLB is read out here, otherwise undefined. HT for the lookup. HT is equal to 1 TLB hit. HT is equal to 0, no hit. Okay, whenever the ST is equal to 1, a TLB hit, or when ST is equal to not 0, no hit offer. For right, ST must be 1. To write the ST bit must be 1. REP is bit is there. For right, select associative blocks of the TLB for the lookups. ST is equal to 1 represents in which a TLB is equal to 1 is for otherwise undefined. Test operations. To write a TLB entry, move a double word to TR7 that contains the desired physical addresses. ST and REP values. The ST must contains a 1. REP must points to associative block in which to place the entry. Move a double word to TR6 that contains the appropriate linear address and values for the VDE and a W. Be sure C is equal to 0 for a write command. To look up a TLB entry, move a double word to TR6 that contains the appropriate linear address and attributes. Be sure C is equal to 1 for a lookup command. Store TR7. If the ST bit in a TR7 indicates a hit, then the other value reveals the TLB contents. If ST indicates a miss, then the other value in a TR7 are indeterminate. The test operation to write the TLB entry, move a double word to the TR7 register that contains the desired physical addresses. ST and ARIP values. ST must contain a 1. ARIP must point to associative block in which to place the entry. Move a double word TR6 that contains the appropriate linear addresses and the values for the VDU and a W. Be sure C is equal to 0 for a write command. To look up a TLB entry, move a double word to the TR6 that contains the appropriate linear address and a attribute. Be sure C is equal to 1 for a lookup command. Store TR7 if the ST bit in a TR7 indicates a hit, then The other value reveals the TLB contents. If ST indicates a miss, then the other value in a TR7 are indeterminate. Part 2, that is the debugging. The debugging features of the architecture. The features of the Thread 6 architecture that support the debugging are reserve debug interfactor, the 4 debug address register, a debug control register, debug status register, trap bit of the TSS. These are the some of the features that supports the debugging in a threads. A reserve debug interfactor permits the processor to automatically evoke a debugger task or a procedure when an event occurs that is interested to the debugger. 4 debug address registers, which permits a programmers to specify up to 4 addresses that the CPU will automatically monitor. Debug control register, which allows the programmer to selectively enable various debug conditions associated with the 4 debug addresses. Debug status register, which helps the debugger identify conditions that causes the debug exception. Trap bits of the TSS, T bit, the permits monitoring of the task switches. Trap bits, resume flag of the flag register, which allows an instruction to be restarted after a debug exception without immediately causing another debug exception due to same condition. Single step flag, which allows a complete monitoring of the program flow by specifying whether the CPU should cause a debug exception with the execution of every instruction. Breakpoint instruction, which permits a debugger intervention at any point 3 program execution and aids the debugging of the debugger program. A debugger can be evoked under any of the following kind conditions: task switch to the specific task, execution of the breakpoint instruction, execution of every instruction, execution of any instruction at a given addresses. The debugger register, as shown in the figure, DR0, DR1, DR2, DR3, DR4, DR5, DR6, DR7, DR7, DR. These are the debug registers which are used for various purposes. Thank you friends for watching the video.